Hello, Professor Hahn.
Hi, let me turn my camera on.
Hi, I am Antik. Can you hear
Hi,
me?
nice to meet you.
Yeah, nice to meet you too. Yeah, it is a pleasure to have you uh, give this talk in our department.
Thank you. Yeah, I appreciate the invitation. Hold on, I'm going to adjust the light. It's bright in here.
It's early morning in Arizona, so
Yeah, it's 8:30 here, and so the kids just left the house.
okay,
So
okay,
good timing.
yeah. Have you been to? I mean, we are kind of doing hybrid seminars as well, but uh, because it was a late notice, I thought it would be better if I do virtual.
Yeah, that's fine. I don't know if I would have been able to do it otherwise, so this is
Sure.
good. Yeah,
Okay.
we're doing the same thing here. And I have been to Purdue once. I gave a talk many
Mhm.
years ago at the business school.
I see. I see.
Um, yeah, but
Yeah,
it was nice.
it's cold over here, so I guess it's better to do on.
Yeah, it's the best year. It's the best time of year here, actually.
Okay, so it's not hot and not very cold, or
Yeah,
like.
that's right. So in the mornings, it's about 40 Fahrenheit, and then in the afternoons, it's about 65 or 70
Oh, okay,
on
that's
the
nice.
holiday. So yeah, it's nice.
Yeah.
Definitely. So how many, I mean, I guess I'll find out in a moment, but how many how many people are we gonna have?
Well, if usually we get more than 70 to 80 participants. So
That's incredible. Yeah,
yeah.
you're a very large department, I noticed.
Yes, 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 yes. And
Um,
part of this
I knew
is,
that.
yeah, say that again.
I said I knew that, but
Mhm.
when I went and looked again this morning to see who I was going to be talking to, I was surprised again.
Yeah, yeah. So it's a large department, and part of it is due to that this seminar is a course for our students as well. So students who get a credit for attending this seminars. So
Okay,
mm,
good, very good.
lots of faculty also join. So
All right.
we'll start in about couple of minutes.
Yeah, no problem. And you can see my slides
Yes,
and
yes, yes, yes.
everything.
Yes, yes. I can hear
Okay.
you clearly, and I can see your slides. I guess
Good.
you are also able to move your slides if we can.
Let me make sure. Yeah, good point. Yeah,
Yeah, yeah. Yeah,
great.
works.
Does this get posted somewhere?
Uh, right. So uh, we usually have a recording of the talk. If you want, I can share the recording with you. So
I might want to give it to some of my students.
sure,
Uh,
sure. I'll share the recording of your talk after the after
Great,
you
thank you.
talk and.
Thank you.
Mhm.
You're giving this. You're seeing the third version of this talk.
Okay.
I've given it at Rice,
Uh-huh.
and I gave it last week at BYU.
I see. I see. I see.
So hopefully this version, hopefully it just keeps getting a little bit better.
Okay. 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 I guess it's related to some of your very recent work, right?
Yeah, so I mean, I was doing machine learning for causal inference.
Mhm.
I had a paper, 3 years ago.
Sure.
And this is kind of follow up on that, where we wanted to
Mhm.
understand a little better what was going on with that.
Okay.
So it's not as cool in some ways. It's not
Mhm.
as like there's no software in this talk.
Okay.
Yeah, but hopefully people will like it.
Okay. So it's 10:30. Maybe we'll wait for a few more people to join in, and then we
Yeah, no
can
problem.
start. Yeah. Okay, I think we have enough people and we can start now. All right, so Professor Hahn, I'll just introduce you and then you can go ahead with your talk.
Sure. Yeah, thank you.
Okay. Hello, everyone. So welcome to today's seminar. It's a great pleasure for me to introduce Professor Paul Richard Hahn from Arizona State University. Professor Hahn is an associate professor at the Arizona State University Statistics Department. Prior to this, he was an associate professor of econometrics and statistics at the University of Chicago Booth School of Business. He received his PhD in statistics from Duke University in 2011, and he also holds a bachelor's degree in philosophy of science from Columbia University. His research interests include Bayesian machine learning for causal inference, Monte Carlo methods, decision theory, interpretable data science, and semi-supervised learning. He escapes Phoenix's scorching summers in the cool mountains of southwestern New Mexico with his wife and 2 young children. Today, Professor Hahn is going to talk about feature selection for causal inference. Please, Professor Hahn.
Okay. Thank you, everybody. It's good to talk to a big group of you this morning. It's nice to be there in person, but it's also nice to kind of be able to give these talks after I get out of bed. It's 8:30 in the morning here and the kids have just gone off to school. And I'm going to talk to you today about some of my research on feature selection for causal inference, which sounds very generic. So let me kind of give you an idea of where I'm going with this. So one way to do causal inference from observational data is to control for confounding. So you do a regression of some sort and you've got a bunch of variables, and a natural question to ask, and the first thing that applied people ask, is which ones should I use? And then once you start doing machine learning as opposed to linear regression or non-parametric kind of regression, you have algorithms that are automatically doing transformations of the variables and transformations of the feature vectors. And what that means is that you don't want to just do variable selection, maybe. You actually want to talk about feature selection. And so I'm making a distinction here between feature selection and variable selection. And where this work is eventually going to go is talking about how to do feature selection. What are the things you have to worry about when you're potentially doing these nonlinear transformations of your variables. Anyway, with that said, a lot of this is a teaching talk. I hope there's some grad students in the audience. This talk should be of most interest to people who want to know more about causal inference, but already have a really good basis in statistics, or people that teach statistics. So even if some of this is familiar to you, maybe I can stir up some ideas in your brain about how to teach causal inference these days to students of statistics. This is work with my student, Drew, who's a very good student. So if you see his name on an application at some point in the near future, or at some point, know that he's very good and that this work is a big part of his dissertation. If anybody, please jump in and ask questions. It makes it more fun for me, and I think it makes it more fun for everybody. So I'll try to be clear and make sense, but please jump in. This is based on 2 papers that are out there on the internet. They're in various stages of submission, I think. And this first paper is about the 3 different frameworks that are used these days, mainly for causal inference. So one of the big things in this talk is that I'm going to try and relate the potential outcomes framework, the structural equations framework, and the causal diagrams framework. And there's been a fair bit written about how these things are different and similar. And what I want to do is do something very basic, which is I want to look at the case of using mean regression for estimating treatment effects, which is like the bread and butter of a lot of applied analyses. And I want to show you that those 3 frameworks all basically have the same content for that special case. So I'm not saying that they're the same, they're different in various ways, but in that particular case, what they have to say about that basic case is actually very similar. And it's really nice, I think, to be able, in a teaching context, to say that. And then there's another paper that dives into it with more of a variance analysis. Okay. So let's kick off finally. Okay, so like in a Stats 101 class, what you might hear is basically to distinguish a causal relationship from a mere association, we have to control for confounding. That's kind of the phrase that's used. And let me just give you some examples. This is all kind of basic, but does eating kale reduce blood pressure, or is it just yoga and half marathons, right? It's the same people that are eating kale smoothies are also doing yoga and running half marathons. And that's a problem, because if we looked at the association between kale and blood pressure, we wouldn't be able to distinguish between the yoga and the half marathons. Does driving a luxury car give you a good smile, white teeth, or do rich people just have good dentists, right? Rich people have nice cars, rich people have good teeth. For a less silly example, one that's been studied for decades, is does preschool improve adult sociability and life outcomes? Or is it just that kids from stable homes are the ones that are going to preschool? So is it a cause or is it an effect? And is there common causes? Like, these are the things we're trying to deal with. So I think a lot of you are familiar with that. And of course, online, people say correlation does not imply causation. This is how you win an argument on Reddit or something. But it's not helpful, because at the end of the day, a lot of times all that we have are observational studies. We need to deal with it. So I like to say, we're pretty confident at this point that smoking is bad, but we never did a randomized trial where we made random kids smoke a bunch of cigarettes. So we have to deal with what we've got. So how do we solve this? Again, in the 101 curriculum, what we might say is, well, we're learning about linear regression. So how can we use a linear regression to solve this? And so in this talk, Z is going to be my treatment variable, and Y is going to be my outcome variable. And so Y might be a measurement of how bright your smile is, or how much you've earned as an adult. And Z might be, in this talk, it's going to be binary, and it might be whether you went to preschool or not, or something like that. And the way we talk about this is often in terms of omitted variable bias. Okay, so we write down our linear equation expression, and then if we use ordinary least squares, what we end up estimating is how would the prediction change if I change Z from 1 to 0? And what is the difference between those two predictions? And that's what OLS does, and it's great at it. But if you sort of just do the substitution that this equation implies, this is a one-slide derivation of omitted variable bias. And you can see that what you're actually estimating when you do that, instead of getting tau, which is sort of what you hope the treatment effect is, you get tau plus this difference. Okay, and the deal is that epsilon term we don't get to see, but intuitively, if the epsilon itself changes due to Z and different levels of Z, in other words, if the error is correlated with the treatment, that's the way we would say that, then this term, this difference at the back end of this is non-zero, and that's omitted variable bias. Okay, so the solution, once you have recognized this equation, the solution typically is just include control variables. In a linear regression class, that typically means you add in a vector of x's that include the things that you want, and then estimate that whole thing. The idea being that in that new model, this epsilon, which a little misleading and confusing to students, right? This is not the same epsilon. And the reason it's not the same epsilon is because we have different x's, and this whole thing sort of co-defines the meaning of the various terms. And that's it. You say include it, run it, and you can get the right answer that way. The idea being that now you're sort of stratifying on income level and other fitness levels and stuff like that. And it kind of intuitively seems like it should work. So what I want to talk about in this talk is some questions that this simple, so this like textbook version of the solution to omitted variable bias raises. How do we know that epsilon is independent of Z, given that we can't see it? That's kind of a basic question. Is this derivation or is this result specific to linear regression? Are common causes the sole culprit? So all the examples I gave were basically common causes. And should we just control for as many things as possible? Seems like an obvious thing. If you're worried about this, then maybe you should just add as much as possible. So we're going to do a lot of lifting in this talk, talking about this first one, because that's the one that's kind of at the heart of it. But we will answer all of these, and let me just spoil the results. The answer here is no, it's not specific to linear regression. Common causes are not the sole culprit. There's actually much more interesting and complicated ways that you can get confounding. And you absolutely should not just control for as many things as possible. If you do that, you'll get really terrible statistical properties. So this talk grew out of me teaching a class for about 5 years, trying to teach first-year graduate students the basics of these three frameworks. And these were sort of the questions that came up. But at the end of the day, what we want is some practical advice for people that work in industry and applied statisticians when they go to run a regression of this nature. Okay, So the first framework, the first way, we need to introduce some terminology here. And the goal is going to be to take what I consider the more modern ways to do causal inference, potential outcomes and causal diagrams, and relate them back to that linear regression version that we kind of learn as undergraduates. So with potential outcomes, the whole idea of causal inference and treatment effects is phrased as a missing data problem. And it's really nice because conceptually, I think we can all wrap our heads around it. The trouble is that there's two things. There's the world where somebody got the treatment, and there's the world where they didn't. And the fundamental problem is we only see one, okay? So just to add some notation here, we're gonna superscript the response Y with a 1 or a 0 to indicate treated or not treated. And the point that I want to stress is that this thing is bivariate. It's a bivariate random variable, and we only ever get to see essentially one margin. Okay. For an individual, that treatment effect, we're going to denote tau, so subscript I for individual, and we're going to define the treatment effect as the difference. You could look at the ratio or something like that. There are other ways to define treatment effects, but the difference is fairly standard. And it's just sort of like, how much would this person have earned if they had gone to preschool, minus how much would they have earned if they didn't go to preschool. And that thing, and I can't stress this enough, that thing just can never be identified, okay? Unless you add some pretty heroic assumptions. And I think it's kind of obvious why. We only ever get to see one of those two things. The beauty and where statistics and causal inference are related is statisticians know how to do averages. And what we can do here is we can learn average effects as opposed to individual effects. So just to start a fight, just in case, if you ever read a paper, particularly a computer science paper that says that they're estimating individual treatment effects, you should raise your eyebrows and dig into the details, because you can't estimate individual treatment effects almost ever. And you see this. I see this in conference papers every year. My students bring it to me and they say they're estimating individual treatment effects. And typically that's not actually what they mean. So what we can do is we can do averages. So we take an average over some population of individuals, and we're going to be interested in that. And for simplicity here in this talk, we're going to be interested in something called the population average treatment effect, which just says that we want to think about this expectation as being over some hypothetical infinite population of individuals. So that's basically just notation. A lot of causal inference is notation. And so the first thing we want to talk about is, how does this framework allow us to articulate the assumptions that are necessary to do causal inference? And I'm hoping that this is not too boring, even if you've seen this before, because I'm setting you up to hopefully make some novel insights. So the first one is an assumption that I'm going to call consistency. And it says that the observed data is related to the potential outcomes via this kind of gating identity. So Z is the observed treatment, and the two unobserved potential outcomes are like this. And so what this is saying is that the thing that we see corresponds to one of the two potential outcomes, and which one it corresponds to is the one corresponding to whether they got treated or not. So one way that this can be violated, a really simple way, is non-compliance. Like if somebody lies about whether or not they took the drug, then you're going to violate consistency, and that's going to cause problems for causal inference. No interference, this is a little hard to unpack, and so let me just give you the intuitive version. It basically says that the potential outcome that you get to see, or the potential outcomes for an individual, are not affected by the treatment assigned to another individual. Okay, so if I get the drug, that does not affect your potential outcomes, right? This can absolutely be violated if you have students in the same class, right? So if you're looking at whether or not tutoring is affecting grades, if Billy is friends with Sally, then Billy getting tutoring might absolutely affect Sally's grade if they talk to each other. Okay, so that's an important one that we need. And then we've got two other conditions. One is called positivity, which just says that everybody needs to have, like every type of person as reflected in the variable X. So this might be demographic info, and every type of person as indicated by which X they are, so this might be age, where they live, stuff about their parents, whatever, has to have some probability of getting the drug. And basically this is just for when we take that average, if there are people that we're taking that average and including them in, and they literally have no possibility of either being treated or not treated, then that's not a well-defined expectation. And the last one, which is the one we're going to spend all this talk talking about, is conditional unconfoundedness. And conditional unconfoundedness says that those potential outcomes that are independent of treatment assignment if we condition on X. And that's just a probabilistic condition that we need. Okay, so what's cool is that the way that this, and by the way, obviously this has existed a long time. This has nothing to do with me or my student. But what's cool about it is that you can see all four of those assumptions in action, sort of making this work. So we want to estimate the left-hand side here. And that linearity of expectation allows us to write it like this. And so what we're going to do is we're going to show that the individual terms on the right here, the expected value of the potential outcomes individually, can be estimated via something we can estimate. Like, so the thing here on the right is an estimable quantity, right? It's just a conditional expectation. So you basically apply it separately to the z=1 case and the z=0 case. And what I want to run through with you is where all the assumptions show up. So the first assumption, consistency, shows up by substitution. We substitute in the definition right there immediately. The independence assumption, conditional unconfoundedness, tells us that because we have X here, the Z here can be dropped. Okay, so that's the conditional unconfoundedness. The other two are a little bit trickier. Okay, so this one we use definitely. This one we use definitely. The other two show up via things being well defined, right? So we're taking this average here, and if positivity is violated, then this thing actually is not estimable. Because for certain X's, we won't have any samples for the different Z's. And likewise for no interference, it means that this quantity is not actually the thing we're going after in that case. Okay, so that's really great. Like, it looks like this framework, which is attributed to often associated with Don Rubin and Neyman. Very powerful, very generic, and mostly it's notation, but it helps us articulate the things that we need to do causal inference from observational data. Any questions on that? I mean, that's a crash course on potential outcomes. I tried to make it accessible. Some of you, many of you have seen it before. Did I miss anything?
Can I ask a question?
Yeah, I'd love it.
Okay, yeah, hi, yes, yeah, this is June. I'm a professor in the department. So what you describe here, I think many times people talk about conditional treatment effect, but you're interested in marginal treatment effect.
Yeah, so that's actually a really great point. Like, the proof of sort of how this works actually relies on the conditional average treatment effect being estimable at each value of the X's. And so even though the estimand of interest here is stated as the ATE, the average treatment effect, you'll notice that along the way, if those conditions are met, you can actually estimate the conditional average treatment effects at each X. It gets it's a little more statistically nuanced in the case where you have continuous regression models. But certainly in the case where X is discrete, and you can think about this as just stratification, you're absolutely learning the conditional effects as well.
Yeah, but then I think those two are, I mean, I think they're different if you are interested. So for example, they could have conditional treatment effect, but overall the average marginal treatment effect may not exist.
Yeah, that's certainly true. So you can actually, sometimes you can estimate the average even if these conditions aren't met. These are sufficient conditions, not necessary conditions, right? Because in other words, if you have it so that these can't be estimated, but you have particular conditional effects that exactly cancel or something. So that's sort of one math detail. What you are saying, I think, is that they're different things. And we might be interested in one over the other, and that's certainly true. Right. But the way that I like to think about it is that if we focus on the ATE, every conditional average treatment effect is an ATE, just of a shrunk population. So sort of all of the insights about an ATE will apply to conditional treatment effects as well.
Oh, okay, fine. And also the previous model you have at the very beginning, you have a joint regression model, this model. Mm-hmm. This is also different from directly modeling the treatment effect giving X, right? If you, right?
So we're gonna, I will get to that. That's where we're going with this. That's the whole point.
Okay.
This model here makes a lot of assumptions that are sort of modeling assumptions. I can point them out now and then I'll come back to them. So one of them is that the impact is assumed to be linear. That doesn't need to be the case. The treatment effect is homogeneous. That doesn't have to be the case. And so forth. So there's a few of them, but we'll fix that. So
Okay.
I'm glad you're totally there. Those are the kinds of questions that a speaker likes because they mean that somebody is following.
Right, thank you.
That's great. Thank you. Okay, so the next step now is. Yeah.
Professor Hahn, there are a couple of questions in the
sorry.
chat if you want to go ahead and answer them.
Yeah, let's see. Okay, no, so that's a great question. So somebody said, when you mentioned individual treatment effects, are those the same as conditional ATE? They are not. And that was the point that I was trying to make. In most papers, for whatever reason, it's very common for people that are new to causal inference to get really excited about their algorithms and to claim that they can estimate ITE, but ITE and Kate are not the same because one of them has taken an average and the other one has not. Yeah, so I'm not in this talk. I'm going to be mainly interested in treatment effect estimation. There are things obviously that you can do that are weaker than that in various ways. And in particular, there's some interesting work on bounding, which is pretty close to what I'm talking about. But yeah, let me come back to that idea of clustering at the end if there's time. Great, thank you, everybody. Okay. So the next step now is I want to introduce real fast the causal diagrams framework and show that we can get to the same place that we got with the potential outcomes with a little bit more detail. So I'm going to have to do some quick probability review. So in this talk, I'm going to assume that densities exist or mass functions exist and are well defined. So there's not going to be a high level of measure theoretic rigor here, but hopefully you can follow what I'm trying to say. So the review is that we have to understand something about joint distributions, and I'm going to refer to joint densities, although this can be mixed, continuous or categorical or whatever. But the idea, as we know, right, is that we can take a joint distribution sort of represented jointly, and we can string together a sequence of conditionals. And statisticians like to overload notation. So the Fs that I'm using here are completely different functional forms depending on the arguments that they take. But the idea is that this is a marginal distribution that only involves one variable and doesn't ever change. This is a conditional distribution that is conditional on one thing. This is a conditional distribution conditional on two things, and so forth and so on. You're not doing anything in the sense that it's not like you're actually simplifying anything when you write it this way. It's perfectly generic. And it's perfectly generic, just you can go through and just check that if you plug in the definitions of these conditional distributions, everything will cancel and you'll get the thing on the left-hand side. But this is a trick we use a lot, right? It helps us think about how variables are generated, to think about, oh, first you draw x1, then you draw x2 given x1. And for somebody like myself that does a lot of stochastic simulation, this is really a convenient way to think about drawing from joint distributions. And it's going to be key for the idea of causal graphs. So what I want to emphasize here is that this is just a representation that we can always do, and that we can do it in any order we want. Okay, so there's if there are p random variables, there are p factorial ways to write this down. Okay. One nice thing about it is that if you write down a particular one, and then you notice that one of the conditional distributions doesn't involve one of the variables that is ostensibly on the right-hand side, then what you've discovered is that there is a conditional independence going on. And probabilistically, in the stochastic notation, we would write, this equivalence is the same thing as saying that x3 is independent of x1 given x2. Okay, and these are powerful in a lot of ways. So what we've done here is we've just talked about the usefulness of this particular representation. And once we have that, though, we can talk about graphs. So relating a compositional representation to a directed graph is really easy. Essentially, what we do is we look at the variables on the right-hand side of the conditioning bar, and we draw an arrow from all of those variables into the variable on the left-hand side. Okay, so we would draw an arrow from x1 to x3, x2 to x3, x1 to x2, and so forth. Okay, so in other words, you give me a conditional representation of the joint distribution, and I can give you what's called a directed acyclic graph. The interesting thing when you think about it this way is that the acyclicity, meaning that there can't be cycles, arises naturally from the fact that it started as a joint distribution. The directionality is natural because it's also defined by that. So you can just think about one of these directed acyclic graphs. If you generate it from a joint distribution, from a compositional representation, then it just encodes the same information about that factor. As far as terminology, it allows us to talk about which variables are parents of the other ones. It's a parent if it has arrows pointing into its children. That notation makes sense, hopefully. It's kind of cute. You can furthermore talk about ancestors and descendants, sort of using the same terminology. Okay, that has nothing to do with causality. And this is the other teaching thing for graduate students out there. My first hobby horse, my first pedestal was that ITE is different from CATE. And now the second one is that a directed acyclic graph based on a probability distribution, that is a probabilistic graphical model, but it is not a causal diagram. Okay, and the reason for that is that there's as many ways as you can rearrange this as there are probabilistic graphical models, but there's only one causal diagram. Okay, so the causal diagram is a special one among that whole set of possible probabilistic graphical models. And in particular, it's the one that where all of the arrows are assumed to reflect causal relationships and only causal relationships. Okay, and we refer to those types of graphs as causal diagrams. So in other words, among the set of possible probabilistic graphical models, you pick the one and you call that one the causal one. That's the mode that we're going to be using this in. Okay, and it's an assertion. It's an assumption about the data generating process that you're studying. Okay. Now, where we're going to go with this is that the reason that that's helpful is that it allows us to think about using those conditional independencies to find to find subsets of nodes in the graph that we can condition on that will satisfy conditional unconfoundedness. Okay, let me show you how this kind of works out. So here is a causal diagram for a particular kind of process, and this is just an example I made up, and so let's walk through it. Z is the treatment variable, which in this case is going to be maybe hours spent on tutoring or just whether or not you did a particular tutoring program. Y is going to be the student's earnings, maybe the student's future earnings. X1 is parent education, how educated are the student's parents. X2 is the quality of the school that the student goes to. X3 is the parent's earnings. And X4 is the family connections. Okay, so I love this graph. This graph I call the box diagram, and as a teaching tool and as an intuition tool, it's super fun because it is just more complicated than the way we normally think about confounding. Okay, and the story makes a lot of sense. So I hope you guys can argue with me if you think otherwise. So here's the idea: educated parents are more likely to send their kids to tutoring, especially if there's a need, right? Likewise, educated parents are more likely to send their kids to a good school. The good school and the tutoring can both have an impact on how successful the student is later on. Conversely, and along a totally separate path, if the family is well connected, I'll be right with you. Thanks for raising your hand. If the family is well connected, that will make it easy for them to get a job. But completely separately of that, the family being well connected makes it more likely that the parents have money. If the parents have more money to spend, they can afford tutoring, right? Now, here's what I think is interesting about this diagram. If you think about the way we normally talk about control variables, it's notable that X2 has no causal relationship to tutoring, meaning that notice that the arrow is going in this direction, which means the causality goes like that, right? And so another way to think about that is that if we went in and changed the student's school, that wouldn't do anything to whether or not the student needed tutoring, causally. On the other hand, you have the reverse situation for the parent's income. The parent's income is not actually causally affecting the student earnings directly. Okay, I have a question. Go ahead. Yuting? Was that an accidental hand raise? I can't hear you. I guess should I just go on?
Yes, please go on, I guess.
Okay. All right. Okay. So what we want to do, okay, so first of all, let me say something that an assumption I'm making that I should probably have written down. So I am not going to consider any diagrams that have any arrows out of Z other than the one we care about. Okay, so one way that there could be another arrow sort of out of Z is that the tutoring could have some change on the student's behavior, and then that behavior could change the outcome. And the reason we omit those is that those are called post-treatment variables. I mean, statisticians have known about those kinds of things a long time, and we generally don't include those in a regression. I'm leaving those out of the graph. I'm also leaving things that are arrows beyond Y, so descendants of the actual earnings, because those will cause problems. Granting me that, the relationship between a diagram with those kinds of restrictions and potential outcomes is really cool and I think straightforward. So think about what the potential outcomes. So the potential outcome is a random variable, and the potential outcomes are going to be affected by these same things, right? But what are the potential outcomes not affected by? Treatment assignment. And why are potential outcomes not affected by treatment assignment? Because by definition, they exist irrespective of the treatment that was assigned. That's the whole point of sort of what makes them work. And what that means is that if we draw a causal diagram for the potential outcomes, it would look like this. Does that make sense? I hope that makes sense. It's a little tricky the first time you see it, but that's what potential outcomes mean. Potential outcomes are exactly the outcomes in the world where it was set, even if in the world that we get to see it was not set, right? So what Z is here is Z is the observable treatment assignment, and Y1 is the sort of hypothetical outcome. And there's no relationship to that precisely because it's hypothetical. It doesn't have to do with the observed Z. Okay.
Professor Hahn, quick question. So why do you call it CDAG, this one?
Causal directed acyclic graph.
I see. I thought conditional DAGs or something like that. Okay.
Yeah, the C is causal.
Okay. All
Yeah,
right.
thank you. I should have said that. That's right.
No, that's
Okay.
Can I ask you a question too, actually? Sorry.
Yes, please.
Actually, sorry. So you said you can't have arrows out from the Z's to like post-treatment variables, but you could also have arrows from the Z's to the X2s. And are you ruling that out because of the independence assumption that you make?
Yeah, well, right. When I said you could have one that goes like that, and I'm leaving that out, that means that the diagram would be drawn with an arrow from X1 directly to here. So there would be a model reflecting that.
I see. So but you also had this assumption that said the potential outcomes should be independent of Z, right? That was your first assumption.
So here's the deal. So that's what we need, and what we're going to do is we're going to show what we have to condition on to make that true.
I see. Okay.
Yeah. So this is a kind of a poor man's rederivation of Judea-Pearl's backdoor criterion, because the way that Pearl did it is he developed a very intense machinery that handled all of the causality in the graph simultaneously. And dealt with all of those complicated cases of where you have post-treatment variables. And what I'm pointing out in this talk, and what students I think resonate with typically in my experience, is the idea that if you rule out those cases at the get-go, then there's a very straightforward relationship between the potential outcomes and the usual causal diagram. And when you do that, it's actually really easy to see the connection, which is the following. What Pearl says is that in this graph, we need to satisfy what he calls deseparation between these things. Deseparation is that things need to be conditionally independent of each other. But what's confusing is that they need to be conditionally independent of each other if this arrow were gone. And that's the thing that students get tripped up on, or maybe I'm projecting, but I got tripped up on that when I was first learning this material. And it's not true in this case. So basically, if you have a potential outcome, once you plug in the potential outcomes, the Z arrow goes away. And now it's very clear what we need, I hope, which is that we need conditional on some set of X's for Z and the potential outcomes to be independent. That's what conditional confoundedness is. And just looking at the graph and knowing what we do about compositional representation, Pearl's algorithm finds subsets of variables that do that. And the reason I like this graph as a teaching example is that it turns out that there's lots of different combinations that work, okay? So which ones work? All of them will work. So if you condition on x1 through x4, that obviously works. That's controlling for everything. Conditioning on x1 and x4 would do the trick. Conditioning on x3 and x2 would also work. And so one of the things that you learn from graphs as a statistician, I think, is just the very simple realization that conditioning sets, the variable sets that satisfy conditional confoundedness are non-unique. And in any given applied problem, there are many to choose from. And that leads you smack into the question of feature selection or variable selection, which is, okay, well, if there's more than one, which one should we use?
Can I also ask another question here?
Absolutely.
Yes, so I was thinking to wait until you finish, but in case we run out of time.
Yeah, I know.
Yeah, so for this case, x2 and x4, they could also be causal factors. Why you think they're different from z?
Well, they are causal factors, but if our goal is to find the effect of z on y, then what this graph tells us is that, yeah, so that's a conditioning on x2 and x4 would work.
Yeah,
Right.
but you can, yeah, but so okay, so I guess my question would be, I think for each of this graph, you have to specify which causal factor you are trying to
Yes.
yes.
So in this talk, and I take that for granted and I apologize, but like we are pre-specifying the treatment of interest.
Yeah, that's
Yeah,
right.
absolutely. Yeah, thank you for that clarification. And I'm always calling that variable z. If we wanted to think about this as x2 as being z, we would relabel this z and relabel this thing some other x variable, and then we would have a different story. Yeah. Yeah, thank you. That's great. Okay. So once we start asking the question, which variables should we include, the standard work tells us that we have all these different sets, and there's been some interesting work about algorithms for figuring out what. But it turns one thing that's worth emphasizing is that that's not actually there's more going on. In other words, the only thing encoded in the diagram is the factorization of that joint distribution. What is not shown is the particular data generating process itself. In other words, what the F's are that were in that, that breakdown. So the next step, which leads us back to the regression setting, which is the goal here, is to associate a causal model with one of those diagrams. Okay, so to specify the entire data generating process for the purpose of treatment effect estimation, Z on Y, what we can do is we can think about what's called a functional causal model. And what that does is that just expresses in sort of probabilistic equation notation. So this is a random variable, this is a random variable, this is a random variable, but G is a fixed function, okay? And typically we don't know it. Likewise, F is a fixed function. So what this sort of notation here indicates is that if I knew the what's called exogenous factors that were influencing Z, and I knew all of the X values, then I would just be able to put that into a function and it would deterministically give me Z. Okay, so for those of you that are familiar with stochastic simulations, you can think about this epsilon term as being the random number generator, right? So X is specifying the conditional distribution. This is like a uniform random variable. And when you composite those with the function G, you get a draw from Z, okay? The diagram further tells us that we can do the same thing for Y, except now Z shows up as an argument. Okay, so this is an algorithm really that tells us that if I have a diagram and I have ways to generate from these distributions, I generate them, I take those values, I plug them into here, I get a value of Z. And then given the value of Z, I plug Z into that same function, I get a value of Y. So it's just a procedure for generating draws from the distribution described by the causal diagram. The epsilons, those exogenous errors, are not shown, But you can think about them as just floating out here, pointing into every one of the variables. That's what makes them random, right? Is that they've got a little bit of stochasticity that's exogenous, which is a term from economics that's used a lot that just means from the outside. So not only is it independent, it's independent of everything and independent of each other. So those are usually suppressed in the graph. So once we have this idea that we can think about these diagrams as expressing these, if you combine them with a functional relationship, you can just get exact descriptions of the variables. You can then also see how the potential outcomes look. And in particular, the way the potential outcomes look is that you just plug in the value of z to be what you want. So think about how this works operationally. To draw from this diagram, as I said before, first draw from x, given x, draw from z, given x and z, draw from y. To get the potential outcomes, I first draw from x, then I plug in the value 1 or 0, and then I draw from the potential outcomes. So I short-circuited this precisely because I didn't first draw z and put it in, I just directly plugged in the value that I wanted. So in particular, because of the way the graph is structured, the thing to notice is that x is drawn first. It is not drawn as x given z. And that's it, that's why it works. That's why this reflects causality. And I know this is a lot, and if you've not seen this before, this is kind of the point where what seems simple maybe falls apart. But what I'm claiming is that this is a really cool observation that allows us to think about potential outcomes and graphs and causal diagrams in a pretty transparent way. Okay. And now I've only got, 18 minutes? If there are no questions. So this is good. I think I have time. Okay. So the last step is, okay, so now that I have potential outcomes and I have a relationship between those and causal diagrams, and now I have a relationship between causal diagrams and these functional causal models. And so the next step is to show how those functional causal models relate to mean regression. Okay. And so to do that, we're going to take this idea that this function describes a random variable, and we're going to take its expectation. And if we take its expectation with respect to epsilon, the exogenous error, for a particular value of x, that the expectation of that thing, we're going to just call mu. We are then going to do something similar with the y1 potential outcome, which is this thing, except we're going to take that expectation and subtract off mu, and we're going to call that thing tau. So these are just definitions. So I'm using the triple equal sign here to indicate that I'm just defining these things. But the point is that it's perfectly generic. Like once I have a functional causal model, like I had on the last slide, I can take these expectations and make these definitions. And what it means is that I can always express my response variable like that. Okay. And what we have here is we have a mean function that involves x. We have a treatment effect function, which is a conditional average treatment effect function. And then we have these mean zero error terms. And just by the way they were constructed, this is just kind of like residualizing, right? But what's cool is that they're mean zero for every value of x. And if they're mean zero for every value of x, then when I take the expectation over x, they vanish, okay? And this is what I'm calling a mean causal model. It goes by other names and so forth. But what I want to point out is the relationship between this and what we saw way back on slide 2 or whatever with the linear regression case. So notice that the linear regression looks an awful lot like this. So what is different? Well, delta is assumed to be identically 0. In other words, there's no heterogeneity around the treatment effect. Tau is assumed to be constant in x. There was only one tau. This thing generally is not assumed to depend on x, in which case we say it's homoscedastic. And this was assumed to be linear. It was x beta. But this is the more generic version. So we now answered the question, does the controlling for confounding idea, is it specific to linear regression? And the answer is no. And this representation sort of shows us that. What do we need for this representation to work? Well, the important thing here is that the error terms are independent of z. And the reason for that is because the only thing that was defining them, given that X was fixed, was epsilon, which by construction was exogenous. So if the graph is correct, and that describes the data generating process, then that means that the error terms are independent of Z. Okay, so that brings us full circle. We're now able to recognize that the linear regression model with independent error terms, independent of Z, is a special case of this more general kind of mean regression model. The more general one emphasizes a lot of cool stuff. The confounding effects of X don't have to be linear. Treatment effects themselves can vary by attribute, which is conditional average treatment effects. And furthermore, there can be randomness. There can be unobserved, like unlearnable variation, and that's what the ITE is. So if you want to think about going back to that point, this here is a Kate. This plus this for a particular individual is the ITE. And you can see that, you know, it involves an error term, and we're never able to learn individual error terms. Okay. At this point, okay, so let me pause for questions. I have basically I have a couple more points I want to make, but I need to make sure people are with me here. Okay. Oh, yeah, okay, good. She's back.
I have questions. Sorry. So then this model seems pretty general, but very different from from the literature that people just do conditional treatment effect.
Yeah. Yeah.
Okay,
No,
so
I agree with you. This kind of model has been most popular historically in what's called structural equation models by econometricians. Jim Heckman is notable for working with models like this. And because he was doing work in the 70s, 80s, and 90s, he didn't have access at the time to the tools that we have to do nonlinear stuff. And so a lot of times they were linear models. But that body of literature is comfortable with this kind of representation, I would say. But I agree with you that this is not the common way to think about it, but it's the more general one.
yeah, but then my question is for comparison. I think there are pros and cons for each, but then do you have any further study on?
Yeah. I mean, it's a long discussion. I'm actually more than happy to talk to you about it offline.
Yes.
The short version of it that I'll tell you is that I got into this because the paper that I wrote a few years ago using machine learning methods, this was the parameterization that we ended up using because it allowed us to regularize tau separately from regularizing mu, which had really big finite sample benefits in the case that you sort of had a guess as to what the magnitude of tau was. And using a different kind of representation where you would maybe model the potential outcomes separately, which is a fairly standard thing to do, doesn't allow you that sort of control. So it's mainly it's a computational convenience in addition to a conceptual perspective.
But then how about the identifiability of all this mean functions like the one you defined?
Yeah, well, I mean, as long as you are able to estimate this statistical model, then the tau term will be the Kate, and under the conditions, as long as these error terms are independent of Z, you're able to do that.
Yeah, I can't tell which one have a stronger assumptions, which I think conditional treatment effect.
Yeah, let me see if I have, yeah, here. Okay, let me do the next two slides, and that will get me sort of to the end, and then you can come back and tell me if I answered your question. Okay, so the thing about this representation that I think a lot of students, the first time they see it, if they think about it a lot, they think it's actually got no content. And the reason being is that the X that's in this equation is exhaustive, meaning you start out with a causal diagram, and now I'm saying if you condition on X, all of it, all of those X's, that you can learn the treatment effect. And that seems kind of trivial, right? It's just saying that for any diagram you have, if you control for every single thing, all that's left is this, which kind of makes sense that you'd be able to estimate the treatment effect. But what's cool is that you can start out here and then start asking questions about, well, can I integrate out some X's, some of the X's? And it turns out that yes, you can, and precisely the ones you can integrate out are the ones that you don't have to condition on. So in a graph like this, we know that we can condition on, say, x2 and x3. And what that means is that I can integrate out x1 and x4 given x2 and x3, and it still works. Okay, so that's what this next slide is sort of walking through. If you have a conditioning set S, which is very generic mathematically, it's just some function of x that takes on a particular value, then you can redefine the terms like this. And then you have to do a little bit of extra work, because now the epsilons are not exogenous. But the way that the proof works, which I've just sort of hinted at here, is that if S is fixed, then there's a one-to-one correspondence between the two potential outcome pairs and the two error terms, right? So if you look at this, if S is fixed, then this is a constant, and this is a constant, which means that if I change the value of this or this, I get back one of the two potential outcomes. And so what that means is that if this pair of things is independent of X, then this thing has to be independent of X too. So that's really cool. That shows us that there's a direct correspondence between conditional unconfoundedness as represented in potential outcomes and as represented in mean regression models. As you know, so in other words, we have three equivalent ways to talk about this. If the function S satisfies the backdoor criterion in that it picks out a subset of the X's that separate the potential outcome diagram, that would be the way that causal diagram people talk about it. Furthermore, if we have such a function that renders Z conditionally independent of the potential outcomes, that also works. And this is the one that's sort of not as well known, which is that that's equivalent to saying that Y has a mean regression model with error terms that are independent of Z given that function. And what's nice about this is that this version of it is exactly the version that is described to first-year students when they learn linear regression. Right. So it's a little bit of work, like you'd have to sit through my whole talk and maybe think about it a long time to understand causal diagrams and potential outcomes. But the idea is that there's a sort of grown-up version of the Stat 101 explanation, which is that as long as you have a mean regression model with independent errors, you can do treatment effect estimation. So to conclude, what I will briefly talk about. So once you get here, it opens up lots of interesting questions, such as, well, conditional unconfoundedness is sufficient, but is it necessary? And it turns out that it's not. There's a weaker condition called mean conditional unconfoundedness. Because the control sets are non-unique, what's the simplest one? We came up with a mathematical characterization of what the simplest one is in kind of measure theoretic terms, which is kind of interesting. What control set is the best one? What do we mean by best? It's non-constructive, but you can show that there is a lowest variance set or lowest variance function, which is kind of the one that you would want. And I can't go into details because it takes too long, and I just wanted to give you the flavor of it, but let me show you at the end here what this looks like. So we have this definition that I did not state here, but we call it the principal reduction, which is like I give you a set and shrink it as small as you can while still identifying the treatment effect. Then there's the propensity function, which is the probability of receiving treatment given a set of variables that I'm denoting here S. And then the prognostic function, which is just the treatment term, and it's just the two terms that appear in the model as written here. It's this function and this function. And what we were able to show basically is that for any conditioning set that you start with, the reduced version of it will have lower variance than the propensity score, which is pretty interesting because the propensity score is everybody's favorite one, or in biostats, it's very common. And the prognostic one will have lower variance than the principal reduction, provided that the variables that you're including are predictive enough. I can't say exactly what that means, but the practical upshot of this kind of analysis and thinking about it in terms of these mean structural models is that you do want to condition on other stuff. So just going back to the graph here, roughly what it says is that if you had a graph like this and you were interested in what you should control for, you wouldn't want to control for everything because that'd be strictly too much. You wouldn't want to control for x1 and x3 because that would have higher variance than if you controlled for x2 and x4. Okay, so heuristically, the closer you can get your variables to y, the better statistical properties that they will have. And that's interesting from a practical point of view, because as I hinted in biostatistics, propensity scores capture people's imagination so much that people's inclination a lot of times would be to use X1 and X3, which are the variables that are causally impacting treatment assignment. So that's kind of interesting. And I guess the last thing that I will say is just that, one implication of thinking about it this way is that we would say that you do want to control for a randomized controlled trial. There's argument about this in the literature going way back. There was a kind of 2008 paper by Friedman that killed regression adjustment for experiments because he said, hey, it can go bad. But his paper was focusing on linear regression and model misspecification. And Lin, 2013, pointed out that that's not the case. And that's the conclusion we agree with. If you're fitting a non-parametric model and you have it very flexible, so there's no chance of model misspecification, the causal diagram for an RCT might look like this. Z is randomized, so there's no arrows into it, but you have all these arrows pointing into Y. And our theorem, the way that we have thought about this indicates that you actually would like to control for these, if you can. And let me just conclude with a concrete example. If you are at a tech company and you are doing A/B testing on a banner, and you want to know, should the banner at the top of the web page be blue or red, and you're measuring click-through, so Z is banner color, Y is click-through rate, and then you have a bunch of factors. So which do you think affects click-through rate more, blue or red banner or time of day? Right? A time of day is a really big deal in terms of web activity. So ideally what you would have done is a randomized trial where you stratified on time of day and you randomized within times. But supposing that you hadn't done that and somebody had already collected the data, the question is, should you do a regression adjustment for time of day? And I would say absolutely yes. And it's interesting because I've talked to colleagues in tech, particularly these big internet companies, and they have learned this because they had previously been doing randomized controlled trials for A/B testing like this and not adjusting for anything. And they gradually kind of wised up to the idea that adjusting for these large effects has a really big benefit. So anyway, thank you for your time. And I know a lot of it was sort of review probably for some of you, but hopefully you thought it was a different perspective. So thanks for having me.
Thank you, Professor Hahn. An excellent talk. Any questions from the audience? Well, I have a quick question. So when you say we might want to condition on a set of variables, I was wondering, is it possible to know which set of variables we can condition on without knowing the causal diagram?
Right. So there's two ways to think about that question, I think. So one way is, can I learn the graph from the variable, from the data, and then given the graph, make my decisions? And in my opinion, that's a non-starter. It takes so much data to learn the graph because you have to do a bunch of pairwise independence tests that although theoretically it's interesting, it's kind of not feasible. The other way to think about that question is, even if I don't know the graph, can I use the idea of a graph to tell me something practical? And that's our approach, right? So although we did the derivations in this paper for a known graph, the use case we had in mind was you don't know the entire graph, but you start out with a set of X's that you think are adequate. And the question is, from that set of X's that are adequate, can you think about pruning it down to a size that's better? It's still hard, but you absolutely don't need to know the whole graph to take that approach. And that's what my student has been working on.
And is it possible? So when you, I guess at the beginning of the talk, you kind of distinguished between variable selection and feature selection. So I was wondering, have you encountered cases where a function of two variables, if you condition on, let's say, x1 plus x2,
yes,
that's enough? It's
pretty wild. So first of all, like, it's absolutely the case that composite, like if it's the, here, let me show you. So there's two answers to this. So the first one is, if this is your model, right? If it's the case that this thing right here, so let's assume that tau is constant just for simplicity. Whatever this function is a sufficient control set in that case. And so if this thing is a ratio or a sum or something, that's technically all you need.
Okay.
Which is pretty, of course, you don't know it, right, in advance. It's as hard as learning the original thing. But once you recognize that, it's really notable that, like, absolutely, you can take dimension reduced things and still do causal inference. Okay, the flip side of it is really fascinating, and it's ongoing work. But there's this thing in these graphs that I didn't talk about for time reasons called colliders. And a collider is a variable that you can't condition on without confounding things, okay? And what's really interesting, I don't know how often it happens, but an easy way to construct a collider is to take two variables that are both related, one's related to the outcome, one's related to the treatment, and composite them into a function, and then control for that thing. So in other words, you can actually accidentally engineer a collider. Okay, and so the open question that we've been thinking about is, if you just take some data and you feed it to a neural network and you ask it to find it, is there any danger that the algorithm is actually creating confounding where there wasn't any?
Mm-hmm.
And I don't know the answer to it, but it's a super interesting question.
Okay.
Yeah, can I follow up on that? So when you talk about the feature, which is like the function of x, that is x is your feature,
Yeah.
is that right?
Yeah, that's right.
How do you, what do you mean by selection? How do you?
Yeah, so okay, so the first step is we have the representation, and we know that everything holds as long as we have some function of S. And so that right off the bat is like, variable selection fits into that framework, right? Because a function that picks off the coordinate dimensions is one example of that. So then the question is, can there be other things? And the reason that we are pursuing this is because most of the best performing algorithms in this area are tree-based algorithms. And if you think about what a tree-based algorithm does, is that as it grows down and does the regression tree, it is building a function sort of by stepwise composition. And so from that perspective, the question that we're interested in is, can you modify the tree algorithms with these principles in mind so that they construct features on the fly that are serving the purpose of treatment effect estimation? So we're not trying to do anything explicit in terms of trying to, learn S, but what we are doing is trying to build algorithms that are in the service of treatment effect estimation. And so we want to make sure that as they run, as they optimize or do whatever they're doing, that they're sort of striving to find the optimal control set or the feature selected set. Now, from after the fact, once you have fit that model, then yeah, it's a really interesting question, because you can go back and take those fits and say, okay, what are we actually conditioning on from a perspective of like, what was the function that we ended up using? Yeah, sorry, I should have started there. Let's say that you have a machine learning algorithm, you fit one of these mean regression models, and you get back a bunch of predictions, right? From those predictions, you can reverse engineer what the conditioning set is in terms of a feature function. And oftentimes that might be of supplemental interest.
It'll be interesting to know the features versus variables. Yeah, I guess that's pretty. I think they're a long way to go.
Yeah. You're exactly right, and that's the point. Like, it would be really nice to run a regression adjustment that was flexible, so you didn't have to make assumptions, and then at the end of it say, okay, well, what was the conditioning set that I was implicitly using when I ran that? Yeah, that's exactly right.
And
Thank
also,
you.
yeah, sure. Just a quick short question about in practice when you do the causal effect or the treatment effect in this model. So you still basically just do multiple regression, is that right?
Yeah, it's non-parametric multiple regression is all you're doing. It's a little challenging just in that there's an interaction term here, right, between tau and z effectively. And so, but yeah, you're right. It's a highly flexible multiple linear regression. And that's kind of So if I go back to the very start, that's what this paper, right? What we're thinking about here is like, what are the formal justifications for mean regression to do causal inference? But yeah, you're absolutely right. It's
Okay, right,
just mean
thank you.
regression. Yeah.
It's interesting.
Yeah, if anybody has questions that you don't think of now or that you don't have time for, feel free to reach out to me. This is ongoing work, and I like to talk about it.
All right. Thank you. Great discussion and great questions. Thanks, Professor Hahn, again for the excellent talk. Our department, I'll see you next week for our seminar. Thank you. Professor Hahn, I'll send you the recording link after it's.
Yeah, I appreciate that. Thank you. All right. Thanks again, everyone. Have a good day. Good weekend.
Good weekend to you too.